Alright, so after we learned so much about self-supervised learning, let's actually try it out in practice and implement the contrastive learning technique SimCLR. So we will tackle this in two parts. In this part, we will be talking about the pre-training with SimClear. And then in the next part, we will be actually using this pre-trained model and fine-tune it on a target dataset. So to keep things simple, we will be using our Cypher10 data module here. So this is not strictly unlabeled data. We will just treat it as unlabeled data. It's just to keep things simple so that we don't waste time, let's say, on preparing a new data set. However, as an exercise later, I will also prepare something for you where you get to experiment with an unlabeled data set, where you then pre-train the model on an unlabeled data set and apply it to this labeled data set. Okay, let's dive in here. So first, again, of course, our imports as usual. And then let's load our dataset, the Cypher10 data module that I just mentioned. So now comes the interesting part, implementing the image sampler. So as you recall from the lecture slides, what we are interested in is creating different augmented versions of that same image. So we will need a data loader that creates two augmented versions of each image. So how would this look like? So we can define a class, let's call that class augmented images, which accepts some transformations here. And then we apply these transformations twice, where X is essentially the image. So we transform the image here, and then we transform it again here. Note that here transforms is something we have to define. So how do we define our transformations? Of course, they have to be random. So when we have random transformations, that's how we ensure that these are different. So I will go with a pipeline that is essentially explored in that paper, where we have a selection of different augmentation techniques. Let me just paste them in here. So what we have is the random resized crop that we are already familiar with, random horizontal flipping, and then a random color jitter. So here we are applying different color modifications with the 80% probability. We are with 20% chance flipping this image to grayscale, and we add a Gaussian blur here. And then of course we are also converting our image to a PyTorch tensor. So, but before we implement the model, let's actually take a look at how these modifications look like so that we get a better feeling for this image sampler. So we are going to use our augmented images with our new transformation pipeline here. And then we are going to create paired images for visualization purposes. So here what happens is when we use our augmented images is that it will create a batch with the first augmentation and a batch with a second augmentation. So this first batch of images corresponds to the first transformation, and this second batch of images corresponds to the second batch or a second set of transformations. However, for visualization, it might be easier to see them really side by side. So here I'm creating a list, and then I'm iterating over these images from each batch and just add them one after the other to this paired images here. It might sound super complicated when you look at it like this, but if I show you the visualization in a few seconds, I think you will see immediately what I mean by that. It's like the image sometimes says more than 1,000 words. So let's take a look at our visualization using Make Grid here from the Torch Vision utility library. So what we can see here is we can see these pairs where for each image we have a pair. So we have, for example, this horse here. So the horse is in two different versions, two different random transformations. Same thing with the deer here. So you can see sometimes these are really the same, let's say deer, but they look very different. The color is different, the position is different. Here it's also randomly horizontally flipped and so forth. So we are creating all these different versions of that image, and the model has to learn that these are essentially the same image. So speaking of the model, let's actually now implement the model. And for that, we are going to use two fully connected layers instead of one. And the output layer will not be returning class labels, but these embeddings. So let's get started with that. So here we are going to load a model from Torch Vision again. We are going to use our small ResNet model because it's faster to train, because I'm also not that patient. It's because waiting half an hour is okay, but waiting a few hours Yeah, that would be a bit too much here. But if you are interested, you can of course also try bigger models. So we are not using pre-trained weights here, because we are going to create that pre-trained model ourselves. So, and I mentioned we are using 2 fully connected layers. So let's set up our sequential here. So FC, that should be familiar to you from the transfer learning lecture, where we are replacing the last layer. That is the FC, the fully connected layer of this ResNet 18 model. And we are using 2 fully connected layers. So we have the first one. We are using 512 hidden units. So we are going to transform 512 to 512 here. And then, yeah, we need our nonlinear activation function. And then we have our second hidden layer. So, and I should emphasize, these are embeddings, not classes. Because here we really want to produce embeddings, and later on when we fine-tune that model, that is when we train the classifier. Here we don't have class labeled, so we are not interested in supervised learning. So next comes the interesting part, the info and CE loss, which we use for SimClear. Oops. For that, I actually also recommend this excellent tutorial by Philippe. So this is an excellent tutorial explaining everything, let's say, in more detail. Here I have a simplified version of that, where I'm, let's say, using a simpler code to show you only the main parts. So let's get started. So we have first the cosine similarity that we compute here. So here this cosine similarity is computed between all features in the batch. However, since the cosine similarity between a feature and itself is always 1, we also need to mask out these values, these ones, to avoid the model from learning to predict the trivial solution where it's just predicting this feature itself. So for that, we are going to add some code here to mask out these ones, where we have total cosine similarity between 2 identical images, essentially the diagonal. So in fact, we are setting the diagonal elements to true in this Boolean mask. And then we use this mask to set the cosine similarity values to a large negative number here, minus 9 to the power of 15. So it's a very large negative number, like 900 million. I would have to look this up again, 15. Using the masked fill function here. So the next step then is to find a positive example for each feature in the batch. And we do this by shifting the mask that we just created here. So we have this Boolean mask here. And here. And by that, right now we are shifting it by 2. So batch size divided by 2, this corresponds to this part here, where we are skipping over from the first batch to the second batch. So remember when we created the paired images, that we had them side by side. Now we have them concatenated. So for example, if we have a batch size of 64, where we have 32 images from one transformation concatenated with 32 images from the second transformation, the image in position 1 would then correspond to the image in position 33, where we have then this positive example shifted by 32 images. And then we can compute the loss here. So this is the info NCE loss. And the info CNE loss is then calculated by using the positive mask that we have and the cosine similarity values. And the cosine similarity values are divided by the temperature parameter here. So we have this temperature, which then helps us to control the scale of the similarities. It's essentially a normalization factor. And the loss itself, the NLL here, let's say that stands for a negative log likelihood. The loss itself is defined as the negative log likelihood of predicting the positive example. So this is calculated by taking the negative of the cosine similarity values that are corresponding to the positive mask, and then we add it to the log sum exponential term. So we have the log sum function here, which essentially is a very efficient implementation of a log sum and then exponentiated. And we apply that to all the cosine similarity values here. And this is the last dimension. So we're applying this to the to this cosine similarity values of along the last dimension. So that would mean essentially for each feature in the batch. And then we are averaging the results here. Yeah, and then we are combining the positive and the negative cosine similarity values. I mean the cosine similarities for the positive and the negative examples. And we are going to use that actually for this sim arc sort here, this which we are saving. We need that later to compute the accuracy. So this arc sort function is then used to find the index of the minimum value along the last dimension, which again corresponds to the position of the positive example. And we are going to use that to compute the accuracy that we, let's say, want to track to see if we make progress during training. So that's then return the loss. So the loss would be this value, and then our sim arc sort here, which we will be using, let's say the positive index, to determine what the accuracy is during training. So it's essentially for the loss and the accuracy here. So in order to, let's say, do this, it deviates a bit from our supervised learning objective that we usually had when we had the cross entropy loss and the classification accuracy. We do have to update our lightning model a little bit. So yeah, so for that we are going to implement our lightning model SimClear version here. And the only difference in this init method to before is that we have this temperature scaling factor here. The rest is the same. We still need a learning rate and we still need a model here. Now, yeah, the forward method is also going to be exactly the same. We again have the same forward method that we used before. The new part here is the training step. So the training step will look slightly different to before. So for this training step here, we now sample still the images and the true labels, but actually we don't know the true labels. We can actually comment them out here. They are just here because we have the Self-Attend dataset, but let's say if you use the unlabeled dataset, you wouldn't have image labels, and we don't need them for the pre-training here. The other thing is now that images has these two batches, the two transformations. So here we are concatenating them into one batch. And then we are creating our transformed features using the model. So self here would call the forward method, which would call the model, which is the PyTorch model, to create the embeddings. So these would be our image embeddings here, the transformed features. And then, then we apply our info NCE loss. So what we are going to do now is we are computing the loss and then this sim arc sort variable that we defined earlier. And we are calling the info NCE loss on the transformed features, the embeddings, in training mode, and we compute the temperature scaling too. So we provide this temperature hyperparameter here, and then we can track the loss during training. So we will use self.log to train the loss. We will also be tracking the training accuracy. So here the training accuracy is not the classification accuracy, so that's really important to emphasize. I'm not sure how to call it otherwise. Let's just call that training accuracy, but it is really a different interpretation. So here, when I say this, we are looking at the top five most similar examples in the batch, and we basically check whether the top 5 examples contain the correct image batch here. And then let's also return loss for optimization. So this is what we are optimizing here essentially. So we don't need to return this because this is just for monitoring. We are not optimizing this. I mean, it's implicitly optimized, but we are using backpropagation only on the loss here, the negative log likelihood term. Then our validation step will also look slightly different. So I could have created a shared step because these are exactly the same as here. So we can maybe also, for clarity, comment these out. And then we are also again calling our info NCE loss, and just for tracking purposes, we also apply this here. I set it to equal 0. You can do that. It's essentially a little bit more harsh. So this would essentially mean the top 1 accuracy, whether the first batch would match the correct batch essentially. But we can also change that to smaller than 5. It's really up to you. I think I would probably keep that consistent. So let's also change that to this to make this consistent. And then we can define our optimizer. So the optimizer here, yeah, you can use SGD or Atom, that's really up to you. So I use Atom here, which is sometimes a bit easier to optimize, so we don't have to fiddle so much with the different learning rate values. Yeah, and then let's actually train this thing. Let's define our Cypher 10 module here. And then we are instantiating our lightning model. So this lightning model is instantiated using our PyTorch model that we defined earlier as a ResNet 18. And then we can use the same trainer class as before. We will use the CSV logger too, so that we can visualize the results here in this notebook directly. So let me actually execute this so I don't forget later. And then we can call trainer.fit as usual. It's one little mistake. Let's check that out. Yeah, I always forget to execute something. So let's do this again. So this might take a while. So I'm skipping ahead here where I already ran all the training and we already have everything pre-trained. So let's assume the trainer fit method finished after some time. Then we can use our familiar plotting function here. And as we can see, the training loss goes down over time and the validation loss goes down over time as well, which is good. That's what we want to see. So that looks really great. And then we can also see that our accuracy here, our top 5 accuracy, also looks pretty good. So we can conclude the model was pre-trained well using our SimClear method. So we then save our model. So here we are saving our PyTorch model. Let's call that SimClear ResNet 18. And then in the next video, we are going to use that model and fine-tune it for classification. Yeah, so in this video, you learned about SimCLR, which is a contrastive learning technique for self-supervised learning. And as we have seen, this is yet just another way that helps us to leverage large models.